So thanks for coming today, and is it too loud? Chris, is it okay? Okay. All right. And just give you a brief outline of my talk here. And as I'm giving my talk, please feel free to interrupt with any questions, because my goal is to communicate with you and to sort of convey some knowledge to you. And if it's not sinking in, please stop me and ask me some questions. I can help clarify it. So I'm going to talk today about virtual high performance computing. Here's a brief outline of my talk. First, we're going to talk about the motivation for the use of virtualization, give you an overview of virtualization technology, an overview of cloud computing technology, and then how cloud computing technology relates to HPC. I'll give you some practical notes from my own experience on virtualization and cloud computing, and we'll talk about some virtual HPC clusters and how to get started. All right. So why virtualization, and when does it make sense? So there's been a trend that's happened over the last 5 or 6 years, in which the clock speed advances made possible by Moore's law just aren't happening anymore, okay? Reaching some fundamental physical limits. So in the past, you could write a program, run it on a single processor, and you got a free speed increase every 18 months from Moore's law. It was great. Things would just go faster and faster and faster. What's happened over the last few years is because of the limits of Moore's law, we're going to multi-core computers. So what's happening is processors are getting more and more and more cores, but the cores aren't really getting any faster, okay? And that's kind of changing the basic dynamics of how we can use computers for science and engineering applications. So there's a new processor called the Intel MIC coming out, or MIC, and I got a little icon there. It's the Xeon Phi processor, and it's going to have 50 plus cores on it. That's a huge amount of cores, okay? That was a supercomputer not so long ago. And also, because the core footprint is increasing, the size of the memory on each motherboard is increasing as well. So today you can get 512 gigabytes on a system. So imagine, being able to buy a single server. You can put a 1U in a rack that's like 55 cores, half a terabyte of RAM. That's a little supercomputer on its own. So what's happened is that, the approach in the past that was used for applications, especially for administrative applications, was to tie a single application to a single server. The idea was you'd have racks full of servers. Each application was sort of be homed on its own server to try to decouple the applications from each other. So in case an application began misbehaving or a server crashed, you wouldn't take down the whole enterprise. So in the past, each application run its own OS image and server for manageability and serviceability independently. Well, it just doesn't make sense anymore if I have 50 plus cores, right? It doesn't make sense to have a single threaded application running on a server when I have 49 cores sitting idle. So it's difficult to share an operating system in various library versions, running the multiple apps in the same system if the OS and library version requirements are conflicting, okay? So if I have a set of applications I want to run, I think, I'm going to put them all on this one multi-core server, I immediately run into a barrier that, well, application A needs this version of the library, application B needs the other version, well, how do I put both on? It just doesn't work. So what you're seeing is that virtualization technology is being used to partition large-scale servers to run many operating systems and VMs independent of each other. So it's basically partitioning up the system. And what's happened now is that virtualization has really become a commodity technology, just like commodity processors, like GPUs, like RAM. I mean, most, the top 500 systems, you can go down to Fry's and buy a lot of the parts they use in those systems. Okay, that wasn't true in the past. So virtualization is not really old, not really new. It's been around since the 1960s. IBM first invented it. It's for partitioning up some of their mainframe systems. And so what you see today is that this technology is commodity. It's used for financial applications, for administrative applications. It's very much mainstream. And it's representing a commodity trend that's worth exploiting, just like other commodity trends we see out there in the computing industry. And it's a especially useful substitute for small-scale lab clusters that are used really in the life of a life cycle of a parallel application. So what we see is that scientific applications often go through a life cycle. They start first as a single processor in a single system, and then people try to run them parallel versions for like a parameter sweep, and they think, well, let me do some domain decomposition and let's run it in parallel. So it kind of grows over time. So what you see is that, and there's a certain point in their life cycle where people tend to have like small clusters, where they, like 10 PCs under my desk, or something in my lab. Virtualization is a great technology just for that space right now. You can use it right now for that. So as your software kind of grows and evolves over time, it requires like a functional ecosystem in which to run, okay? So it's kind of like Maslow's needs hierarchy. So in the basic level, you need a reliable computing platform, a functioning operating system platform that's needed by the application, with adequate disk space, memory, and CPU cores, okay? So over time, as your software evolves, you need this kind of very stable environment. There's also safety needs. You need a secure computing environment, no attackers, a sense of security and predictability environment that you're using. I mean, if you're running your application and benchmarking and debugging it, and someone's changing your libraries underneath you, it's going to really mess up your application. So that's kind of a safety problem there. And also a sense of community. All the nodes in the cluster, when you build a cluster, need to be consistent. MOS version, libraries, and especially critical for MPI applications. So meeting these needs ensures a consistent software ecosystem for your application to sort of grow and expand into. And a stable platform facilitates software development, testing, and validation. And it gives the community of users and developers a sense of security about they can trust the software and the results from the software, more than if the OS and the libraries are always changing. And it provides a strong base. So the problem is that over a period of years, if you use often when you use a large shared system, it's difficult for users to control their computing environment for scientific applications. So there's a good example that the Large Hadron Collider project, the sub one called the Compact Muon Solenoid project, the CMS project, they have an application that has lots of requirements about the libraries, the operating system. They actually have their own sort of brand of Linux, scientific Linux they use. We use actually Red Hat at Purdue, which is close enough. And so they'll require a lot of specific applications, packages, and versions. And it's a lot of work for a central IT organization to keep all that kind of running and installed. Also, as I mentioned, another problem is that scientific applications go through a life cycle where they evolve from a single processor into larger and larger cores and finally to a large-scale system. And if you try to build small-scale physical clusters as part of this life cycle, it's very expensive in terms of equipment, time, and wasted effort, basically, running these systems. And also, from my own experience, usually when you're in that life cycle of going from a single processor to starting to parallelize it, having some kind of level of root access on your own operating systems is really nice to have. Does anyone here run their own clusters or run Linux? Does anyone here run Linux? A few people? All right, cool. Does it sound familiar to you, what I'm saying? Yeah, all right. So virtual HPC clusters are really an attractive and a viable alternative to small-scale lab clusters for applications that are still young in their life cycle. And on a larger system, virtual clusters are a really good approach, a promising approach to provide system-level checkpointing for large-scale applications. So imagine a scenario where you could use a virtualization on your laptop to develop 2 or 3 VM cluster virtual clusters. And then with everything you need, and you get all packed up and you send it up to your large virtualization system to kind of expand out. That's kind of the goal here, or the vision. So on a smaller scale, there's a good place for virtualization and kind of replacing the lab scale cluster. On a larger scale, virtualization is a really promising approach for doing a version of what's called checkpointing. And something that you should think about when you're writing your applications is reliability. It's a really important problem today. In your application, in its life cycle, as it grows up from being a single processor to a small-scale cluster to a large-scale system, what happens is the poor reliability of large-scale systems causes frequent failures. And parallel applications that rely on the long-running, stable running of platforms, basically when one of your worker nodes fails, you often have to restart the whole application. So in your development of your code, while you're working on it, think about reliability and fault tolerance. We'll talk about it a little bit. So one approach that's used is something called checkpointing. Let me back up a little bit here. Yeah. So when you take a look at checkpointing and learn about it. When you look at checkpointing in applications today, there's several levels of checkpointing that are done. One is on the application level, in which your application saves critical program data, and when it restarts again, it looks for the existence of that data and basically brings it in, restarts the computation from that point. Another area of work is on the system level. So there's a system called BLCR, Berkeley Checkpoint Restart, and also Condor has some of these functionalities where it tries to do it underneath the application. The application doesn't necessarily need to know what's going on in terms of reliability, but it's tough to use. It sometimes doesn't work well. Another area of work is below the system level. We actually have a VM container running your parallel application. You actually save that as your checkpoint image. Okay, so you can save all the state, all the open file descriptors, all that kind of stuff. So there's some work going on in that.